Today, let's discuss the uniform convergence of the Fourier-Haar series of the continuous function f. And let's recall that we have proved this theorem for the particular case when n equals 2 to k, the k power of 2. So, if f is from C01, then its Fourier-Haar series converges uniformly to f on 01, and in particular, the following inequality holds. Where omega is the modulus of continuity. Now, we take n equal 2 to k plus I, where I is from 1 to 2 to k, and k takes the values 1, 2, etc. And we also recall that for the case n equals 2 to k, we had rho Cfn less than or equal to omega 1 over 2 to k f here, when n equals 2 to k. We will use this estimate in the process of the proof. So, first of all, let's find out what is the form of the nth partial sum of the Fourier-Haar series dependent on the location of x. If x is from 0 to I over 2 to k, let's find out what is the form of Sn, and then the form when x is from I over 2 to k, 1, and finally when x equals to I over 2 to k. So what is this point I over 2 to k? Let's discuss the following Haar functions: chi 2k plus 1, and then chi 2k plus I. The next one is chi 2k plus I plus 1, and the last one chi 2k plus 1. So I over 2k is the right endpoint of the support of this nth, in our case, n is 2k plus I, nth Haar function. So what is the support? Is this dyadic interval delta ki, which has the form I minus 1 over 2k, I over 2k. Therefore, we can now see that I over 2 to k is the right endpoint of this dyadic interval here. And when we take x to the left of this right endpoint, this means that all these functions here, from 2k plus I plus 1 to the last one, the 2k plus 1, all of them turn into 0. But the difference between is 2k plus 1 fx and the nth partial sum, n is again, let's recall, it is 2k plus I, is the linear combination of these functions. I mean, these functions, each multiplied by the corresponding Fourier-Haar coefficient and taken, their sum taken. So, this difference turned into 0, therefore we can have the first line of the expression for Sn. If x is to the right of this right endpoint, this means that the first I Haar functions, I mean the following Haar functions from 2k plus 1 to 2k plus first, to 2k plus I, all of them turn into 0, but their sum multiplied by the corresponding coefficients each is the difference between Sn and S2kfx. Therefore, we have the second line for the expression of the nth partial sum. And finally, if x is exactly I over 2 to k, then the nth partial sum is equal to the k partial sum, s2k fx, plus the value of the nth Haar function at I over 2 to k, because the only function out of this the chi 2k plus 1, etc., chi 2k plus I, the only one out of these Haar functions, which is not 0 at I over 2 to k, is the last one, this the nth Haar function. Therefore, I am putting here the nth Fourier-Haar coefficient times the value of the nth Haar function at I over 2 to k at x. Now, when we have the expression for the partial sum, nth partial sum, we can turn to our estimate here. So rho c fn is less than or equal to the maximum of the following three expressions. So here comes rho c f 2 to k plus 1, then rho c f 2 to k, the final case, rho c f 2 to k plus absolute value for the nth Fourier-Haar coefficient, and the maximum value for the nth Haar function, which is 2 to k over 2. Now we have to notice that, we now want to notice that rho c f 2 to k plus 1 is less than or equal to omega 1 over 2 to k plus 1 f. Why is this? Because we have the particular case, and for the particular case we have proved before that the following, let's call this inequality by star inequality holds true, so we used it here. And then this is less than or equal to omega 1 over 2 to kf. Why is this? This is obvious, because 1 over 2 to k is greater than 1 over 2 to k plus 1. And then using a property of modulus of continuity, this is less than or equal to 2 times omega 1 over 2 to k plus 1 f. But because 1 over 2 to k plus 1 is less than 1 over n here, I can have 2 times omega 1 over n f. Once I have this, and also taking into consideration that omega 1 over 2 to k f is less than or equal to 2 times omega 1 over n f, this rho c fn now can be estimated as less than or equal to here. So this is less than or equal to 2 times omega 1 over n f. That second term is also less than or equal to 2 times omega 1 over n f, and this is less than or equal to 2 times omega 1 over n f plus this expression here. Therefore, this is 2 times omega 1 over n f, and plus the estimate for absolute value of CNF, of the nth Fourier-Haar coefficient. As we did it before, this is less than or equal to 1 over square root of 2n times omega 1 over n f, and times this multiplier here, 2 to k over 2. The only thing left to be done is to show that 1 over square root of 2n times 2 over k over 2 is less than or equal to 1. And this can be easily seen. Let's have that last a small estimate here. So by substituting n by substituting it by 2 to k, because n is greater than 2 to k. So if I put here 2 to k, I get something larger. So square root of 2, 1 over square root of 2, 1 over 2 to k over 2, and times 2 to k over 2, which is 1 over square root of 2 less than or equal, and this is less than or equal to 1. Therefore, this is less than or equal to 3 times omega 1 over n f. And now we have that this theorem holds also for the general case.